In the last class, we have looked at optoelectronic materials. So we first started looking at metal semiconductor, insulator, direct and indirect band gap semiconductor. And finally, we study the optoelectronic materials. In this class, we are going to look optoelectronic devices and the fabrication of or the manufacturing process of optoelectronic devices. In this kind of devices, we have essentially two categories. One where you have an incident light where then create the carrier in your materials. So the classic example is solar cell. This is the solar panel, and the photodiode where you can generate carrier by incident light, where the incident solar radiation is absorbed and then it gives you a current. You also have other type where you inject the electron or holes, inject the charge carrier into your device, which then recombine in order to give you light. So the example is LED and also laser diode, where we can generate photon by using charge carrier. Now we discussed what are the classification or what exactly the optoelectronic devices. Optoelectronic devices have mainly three types, that is sensor, couplers and emitters. In sensor, we have a main three category, that is the photoconductive, photovoltaic and photoemissive. What exactly the sensor? A sensor is a device that detect or sense the event or change in the environment and responds to some output on other system. In sensor, we have further three types, that is the photoconductive, we know, and then photovoltaic and photoemissive. We know that in photoconductive means the conductivity of the material increases when the incident light on semiconducting material, or it decreases the electrical resistance by incoming light. We have there are two types in photoresistor. You consider the example is photoresistor, that is the light dependent resistor, LDR, and that you have cadmium sulfide, cadmium selenide and lead sulfide. And further we have a other type, that is the junction type. You call it as the photoconductor, comes under photoconductive devices. Here we have photodiodes, that is the PN junction, one junction, PN junction, pin, or that is PAN photodiode, avalanche photodiode. Another you have the two junction, that is you call it as the photo transistor. Example is bipolar and FET. And the next category is photovoltaic. In photovoltaic devices, there will be a conversion of light into electricity, or voltage. Convert light into voltage. The example is solar cell, that is the silicon solar cell, or selenide solar cell. And next we also have a category comes under sensor is photoemissive, which means it emit the electron when a light is incident on semiconducting material. Example is the photoelectric tube and photomultiplier tube. When a light is incident on the semiconducting material, it releases electron in a tube. In a photomultiplier tube, a tube contains some gases like xenon or neon gas. The released electron or the emitted electron get accelerated towards a anode, and then they hit the bound electron of the gas molecule and then release the secondary emission. In this way, the electron get multiplied and finally the process is continuous. All the electron get participated in the current. And next category in optoelectronic devices is coupler. We have to couple the two optoelectronic devices, which means in fiber optic communication, we call it as the input, that is the sending source, that is you call it as the LED source, that is the sending information, and this LED sensor is coupled to a optical fiber. And then we have another end, that is the output, you call it a receiving end. In that you can attach or couple optical fiber with photodiode. In input side you couple LED with optical fiber. In output side you couple photodiode with optical fiber. And then we call it as the emitters, which means it emits the light. Okay, that is another category. By injecting the charge carrier, and then we can receive or emit the light. Recombination process will be take place. The classic example are LED. This is also a device which emit infrared radiations and laser. Next we go to the fabrication process of optoelectronic devices. Here we consider the example of solar cell. Okay, and this process there are mainly 7 processes. Purifying the silicon, making single crystal silicon. Single crystal means it means whole crystal have the same crystallographic parameters, that is the lattice constant or basis vector, you call it as ABC. Whatever it may be, the angle between along interfacial angle and interplanar distance d, all these are equal in a whole crystal system. That's why you call it as making single crystal silicon, that is the purity. Making silicon wafers and then doping, and next is placing electrical contact, and then anti-reflective coating and encapsulating the cell. Let us discuss in detail the first process, that is the purifying the silicon. We know that for use in the solar cell as well as other semiconductor devices, silicon must be a much purity than metallurgical grade silicon. The standard process to purifying it is known as Siemens process. In Siemens process, the metallurgical grade silicon is converted to a volatile compound, that is condensed and refined by fractional distillation. But the Siemens method produces a polycrystalline silicon, that is the impure molten, that is the impure silicon, you call it as the polycrystalline silicon. We need to get a single crystal silicon. Starting from a polycrystalline silicon, there are 2 different methods for that, for getting single crystal. The first one is floating zone technique, and the second one is Czochralski technique. The silicon is purified using floating zone technique, that is a rod of impure, that is the polycrystalline silicon, is passed through a heated zone several times in same direction. So this produces a drag the impurity towards one end. With each pass at a specific point, the silicon is deemed pure and the impure removed, that the impurity is removed. Here you know that here this is the floating zone technique, where it have a polycrystalline silicon is passed through heated zone. Here there will be a heated coils, and then in the same direction, in each drag with each pass, the specific point the silicon is deemed, and then impurity is removed, and finally we have a pure seed silicon crystal. Now for the second process of making a single crystal silicon, in this process we use Czochralski technique. It consists of furnace, crystal pulling mechanism and control system, and also it contains silicon dioxide tube. The furnace is heated above 1500 degree Celsius. A seed of crystal silicon is dipped into a melted polycrystalline silicon. As a seed crystal is withdrawn, forming a cylindrical ingot of very pure silicon. You know that in this type of technique, here this is the silicon dioxide tube, and here that is the heating coil, the furnace. This total you call it as the furnace. Here this is a polycrystalline silicon. Here finally, after this pulling mechanism, and the furnace is heated up to or above 1500 degrees Celsius, a seed of crystal of silicon is dipped into melted polycrystalline silicon, and then a seed crystal is withdrawn, forming a cylindrical ingot of very pure silicon. Okay, by using this Zolkowski technique, we will get the pure silicon ingot. Now, next process is making a single crystal silicon, and then we have to make it wafers. When a large single crystal is sliced into wafers of about 300 micrometer, and then polished to remove some marks so that it absorbs most of sunlight. Okay, and the next process is doping. It is a very important process. Depending upon what kind of impurity we add for our final application, we can add impurities to silicon wafers with aluminum, boron, or phosphorus based impurity. The wafers are then sealed back to back and placed in a furnace to be heated below the melting point. The melting point of silicon is 1412 degrees Celsius. So finally, below that melting point, finally we get a doped silicon. For solar cell, boron, a p-type dopant, is normally used, and the phosphorus has n-type impurities must be introduced to give a p-n junction. Now when you get a cell, the next point, when you get a solar cell p-n junction, the next very important process is placing electrical contact. Electrical contacts connect each other or each solar cell, okay, both n-type and p-type region, that is the metal contact, to another and to receiver of produce current. The contact must be very thin so as not to block the sunlight to the cell. The metal such as palladium or nickel are used after the contacts are in place. Then a stripe are placed between the cell in order to get complete circuit. They are how we are placing the electrical contact, complete solar cell, and then we have metal contact for the completion of electrical circuit. And then we have another important process, that is the anti-reflective coating. We know that pure silicon is shiny. It can reflect up to 35% of sunlight. To reduce the amount of sunlight lost, an anti-reflective coating is put on the silicon wafer, okay, so that incident light will have large probability of being absorbed into solar cell. The most commonly used coating are titanium dioxide and the silicon dioxide. Sorry for that, I have silicon oxide, that is the silicon dioxide. And the next important process is the last and final process, encapsulation, that is encapsulating the cell. The finished solar cell is then encapsulated, that is sealed into silicon rubber. The encapsulated solar cell then placed into a aluminum frame and then plastic cover. It is very important for a mechanical protection, chemical protection, and electrical isolation. After that, we will connect many solar cells. This is the one complete connection and encapsulation of solar cell. Then we connect many solar cells and to make a module. One module which contain many solar cells, and then connect more than two modules to make a panel. This is, you call it as, this is the module which contain many solar cell, and then more than 2 module we have a panel, and then many panel to make an array. So this is the complete array of solar cell. You call it as the panel. And we have some type of applications. Let us consider one application, that is the grid system. If you use this solar panel, and this is the inverter we have, the electric charge or the electricity will be charged here, and then you can use for your house, and then remaining electricity will go, meter reading will be take place, go to the electric board, or you send to the government also. In some other time, in other seasonal change, you can, if you use the government electricity to your home, the addition and subtraction will be take place. Final, you have, if you give more number of unit to the government, then government you will pay the amount to you, or you can pay. This is a very good system. Here you can, by using this solar cell panel, array of solar cell panel, you can generate electricity and storage, and you can use. After remaining, you go or to give to the government. In next future, it may be the system of grid system in every home. Okay, thank you. Thank you very much.